going over in class?
No, I mean, yeah. No, because I was the crazy person.
Alright, let me see. What do we get?
No, wait.
Yeah.
Alright, so like, I think I did this one.
Didn't you guys write your handwriting lines? Isn't that what you're trying to do first?
Yeah.
Handwriting lines. You need a middle, and you need a top, and you need a bottom, right?
The middle would be -3, right?
The middle would be the first number, which is -3, yes.
Okay. Oh, cool. Okay, so like, start.
The middle would be -3.
Thank you. Oh.
The middle would be -3. Then the top would be how many away up and how many away down. Good.
Since is this 100 plus 2 or is it right? It's 100 plus 2 or is the 2 already out?
I just kept it the same as everyone else's, that way it wouldn't be weird. Okay, so what did we say? Where's the middle?
Middle is down 3.
-3. Then we said how far up, how far down are we supposed to go? Okay, so we're going to go 5 up from there, which is going to land us at 2, right? 5 up from -3. We're going to go 5 down from -3. Where's that going to land us? -8. And what's the point of doing this? Yeah, show where the wave is supposed to go. Where it's going to be cycling around. What's the axis of symmetry, to some extent. And then to see how tall it needs to go. How high it needs to go, and how low it needs to go. How are we on those steps? Those are supposed to be the easy ones. Once you get the hang of it. The very first number tells you where's the middle at -3. The next number, the 5, and either one you look at, the 5, which is being multiplied by the cosine, that's the difference, right? -3 is being added, that's the shift. 5 is being multiplied, that's the stretch. How high, how low our wave is going to go. Now the next two get a little tricky. Do we have these down? Questions on these ones? Middle, top, bottom. Okay. So question. Before we go into the weird pi over 12 and 0 thingamabob, cosine. What's he look like? Starts at the top, and then he goes down and he swoops. Now, is it okay for me to do the normal shape of cosine, or should he be flipped? Normal, because what's the sign in front of the cosine part? Positive. Okay, that's what he's going to look like. So my initial point is going to, initial point, hold on. Where do I get him from? Pi over 12 or 0? 0. Good. So I can go ahead and look at my 0 and say, all right, you're my initial point. I think we were labeling this in our examples yesterday, right? So does my initial point get shifted at all? No. He's going to start on the axis like he always does. But then, how do I use that pi over 12 part? Do you remember? There's a formula for period. Yeah. You could do, there is one version that says 2 pi over b. I think that's what the book uses. But we have to do 2 pi over 12. Doesn't that just sound complicated? So instead we can do the reciprocal, which is 1 over b, which would be 12 over pi. The reciprocal times 2 pi. So what's my period?
24.
Oh my goodness. Good thing we figured that out, or else I think my tick marks would be a little bit off. Is anybody else expecting 24? Not unless you found it, right? So we look at our initial point. We know where to start, but we don't know how to do our tick marks until we figure out our period. Now, kiddos, are we going to do 24 tick marks?
Yeah.
Here you go. What would be a little smarter Where am I actually putting points?
Every fourth.
Every fourth. Okay, cool. So then think about your quarter cycles. From 24, what would my quarter cycles be? Every 6. And where am I starting from again?
0.
0. Okay. So we're going to start at 0, and we're going to go 6, 12, 18, 24. And if I had to go backwards, wouldn't I just go 6 to the left, another 6 to the left? Maybe we won't do the entire other cycle. Now here's where some get really confused. Where's my first point again? At the top. And the top is going to be at
0.
when x is 0 and y is 2. Right? So start at the top. We're trying to recreate this little guy, but in here. So at the top, when x is 0. Now I'm going to move over how much to get to my next point?
1 tick mark.
1 tick mark, which is 1/4 or 6 of my period. And it's going to go in the middle, right?
No.
That's where people get confused though. Where's the middle? It's not at the axis anymore. Where is it?
-3.
At -3. Middle. There we go. Go over another fourth of my period and down, right? Go over another fourth. Go over another fourth, and we're right back up. Have I recreated the cosine curve given the transformations of the equation? Yeah. And how do I go backwards? Yeah, go a fourth, and now you're in the middle, right? Go a fourth, now you're at the bottom. And I could keep on doing that all day, but let's not. Let's put a little arrow and say, yeah, he keeps going. How'd we do?
Terribly.
Maybe initially it wasn't so hot. However, you need to think through what were the pieces that you were missing when you couldn't do it on your own. Maybe you need to go back and remember, review, study what, well that's not the form you like, what each of these pieces stand for. Right? Go back to those places where we labeled, this is our sinusoidal axis, then we go up amplitude, down amplitude. Maybe go through and maybe you should actually number, okay, I'm going to look at him first, then I'm going to look at the amplitude, then I'm going to look over here at the initial, then I'm going to look over here at the period. There really is a system, you just have to study it, or maybe repeat it and practice it. Maybe write down an example that you have in your notes, you know you have the answer on a whiteboard or something, maybe at home. Work through it, try to graph it yourself and say, did I get it right? And figure out what went wrong. Some of you guys study different ways. Some of you math comes to you different ways. Some of you need to actually write it down. Some of you just need to look at it. Some of you need to memorize as much as you can and then see if the pieces fall into place. Okay? But were there any questions or are there any parts that you're not clear of as to how we got the pieces down here? Okay.
I'm not really on the graph, but like the 12 over pi, is that because you had 1 over pi over 12?
Ooh, close. I just did the one, this is my b, right? I used the formula 1 over b, which means reciprocal. 1 over b times 2 pi. And that 1 over always just means flip. So flip the b times 2 pi. How does this problem
Oh
get
no.
kind of weird? You don't have to do a graph, they give you a graph. Interesting. Or you can just find
The equation.
Wait, don't we have a general equation we can start with letters, right? Help me out. Y equals.
D plus a cosine of x minus.
How do you know
A B.
cosine? Isn't it
It says
cosine
in
or?
terms of cosine,
Hold us.
and b minus c over b.
That's just the general one, right? Now we have to think about if this was our graph, if we had done this, where would we look to find D?
D is 0.
How do you know? D is the sinusoidal axis. Sinusoidal axis is the middle. Now, how do you know for sure it's the middle? Look at the top, 2. Look at the bottom, -2. Yeah, isn't that centered around 0? What's different between that one and the one we just did? Wasn't this one a little bit off? Up 2, down 8. The middle was somewhere else. But for ours, up 2, down 2, yeah. All right, Caleb, help us out. helped us out and we figured out that D was 0. Okay, hold on, we have some more stuff to fill in though. I'm gonna keep the cosine, I'm gonna keep the plus, we have to figure out that blank. Keep the parenthesis x minus the. Anybody have any ideas for the amplitude?
2. Gosh darn it.
Why 2?
I don't know why.
How high, x things in the center. How high? 2. How low? 2. Yeah. Remember, this is the amplitude, right? Cosine. What's cosine shape? Where does it start? Top. If it looks like this, and here's why I'm asking this question. Where is his initial point? Where's his initial point? Gotta look at the graph, right? Huh. How many tops do you see?
1, 2.
We can choose either one, technically. Both of them are tops. Both of them could have started. You could have started here and gone, or you could have started here. So maybe there is more than one answer. But which one do you guys want to choose? The one that's farther away or closer to the axis?
Closer.
Okay. So we'll choose it. Wait, where is that? They didn't really label. Oh wait, they did label 1. If that's pi, what would half of that be? Pi over 2. Is this right above pi over 2?
No.
Above pi over 4, just a
Let's
sympathetic.
go in half again. And what's half of pi over 2?
Pi over 4.
Pi over 4. Does that look more like where it was supposed to be? We are making an assumption, but aren't we making it based on the information given as best we can? So if that's pi, that must be pi over 2. Ideally, they would have put a little tick mark and told us exactly where it was. But maybe they're trying to make us work for it just a little bit. Now question, guys, was that to the right or to the left? So do I keep the minus or do I change it to a plus? Keep the minus, because remember subtracting moves to the right. So I'm going to throw in my pi over 4. One more. What does the b come from? Remember, we don't put him straight in the graph. We use him to find who.
Period.
Period. So before I can find b, I need to find the period. Set that equal to 1 over b times 2 pi, or 2 pi over b might be easier to solve in this case. Oh, but you need the period. Question, how do I find the period from this graph? The period is how far from initial point to,
Oh, ending point.
could I do that? Would that work? Okay, but stink. Didn't we say just a second ago they should have split this more? Why don't we go ahead and we split it for them and say, well, you guys are pumped. We'll do it for you. There's that one, there's that one, there's that one. Okay. What are we counting by in our new tick marks?
Fourths.
1/4 pi. You ready? So that's 1/4. How many fourths would that be?
2,
2/4,
3,
3/4,
4,
4/4,
5,
5/4,
6,
6/4,
7.
7/4. What's my period?
7
7/4. Don't forget that.
It's a little bit
It's a little bit further.
Oh, hold on. Sorry, I'm coming at it from a different perspective. You're right.
It'd be 2 pi.
Alright, from my, let's, no, you don't need to put that. Okay, so, as you keep going, what was the answer? 8 pi over 4.
So it's 1.
Wait, what's 8 pi over 4? Worst comes to worst, don't make jumps if you're wrong. Write it down and say 8 over 4 is,
2.
oh, that's normal.
It's 1.
So if that's normal, did it get horizontally dilated at all?
No.
No. So what does B have to equal?
1.
Is that how they're going to have the answer in the back? No, they're going to write it prettier, right? So then if we were to write our final answer, would we write that 0 plus? No. We just keep our 2 cosine. Would we write the 1 times?
No.
No. X minus pi. Dun, 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 dun.
That was not fun.
So if pi over 4 is equal to c over b, why wouldn't b be equal 4?
Oh, because remember, we pull out the b. Why wouldn't B be 4? Oh, because you're saying C is pi, but C is not pi. If we were to go back and write this a different way, how would that look? Another way of writing it? Here we go. With our B and C, I guess we could pull out a 1/4. I don't like that any better. But long story short, you're trying to think of what was C before B got pulled out. But in this case, there we go. According to our period from our graph, B has to be 1. Like B actually comes from the period itself. So B has to be 1. That's a given. That must be true. C over B, remember that's what happens if there's a B here and it gets pulled out. It gets factored away. But since 1 got pulled out, then in a sense, C is pi over 4 and B is 1. Does that make sense?
Okay.
So we don't know for sure who C is. C is just kind of like this extra little piece.
Okay.
Is that better? Question, was it tricky? Yes. Did it take as much work as this one? I don't know. But it was still a little bit tricky. Jason, go ahead. What's your question?
Are they always going to tell you in terms of cosine or sine?
Yes, and if they don't, you get to choose. Which means you could choose the top as the starting point for the cosine, or you could have chosen like this one, negative pi over 4, as the starting point for sine. Just the starting point would be different. Okay. So what if, oh no, what if we're given this one? Now there are words.
I mean, what?
Wait.
Over here.
This one's kind of easy, except one thing. Has anybody figured out that the directions, I kind of just stole them from the page before, and it doesn't really work? Because what they tell you in the words.
In terms of
cosine.
Yeah, I chose the wrong example for my in terms of cosine. In the problem, they say choose sine. Okay. So then you're going to choose sine, not cosine. But it's kind of nice because they tell it to us piece by piece, right? We just need to know where to put it in our general equation. All right, hold on. Who's that general equation again?
You did.
C plus A. Who's going to be here?
Sine.
Sine.
B X minus C.
Someone tell me something.
1 for D.
1 for D. How come?
Vertical translation of
Nice. Now careful. They didn't tell us sinusoidal axis at 1. But the translation up 1 means the center moves 1, right? So, good. We can put in a 1. Let me write the rest of the stuff that stays. Y equals, we're going to put plus. We're going to have a sign, a big space. We're going to have an x minus. All right. Someone tell me something else.
X minus pi over 2.
How do you know that?
Because the phase shift is that.
It's to the right, which means keep that minus, right?
2 for A.
Because it says
Amplitude.
amplitude.
It's 2 for B because
Okay, now that one's trickier. How'd you figure that out, Caleb?
the period is pi, and then the period formula is 2 pi over B. So 2 pi over B is equal to.
Some of you could just see 2 pi over who is pi, these two. Others of you, if you were to solve, I would move that B up and then divide by pi. That'd be a way to solve for it. But yeah, B is 2 because the period got cut in half. Now would they write it that way? Maybe. How else could they write it? They could put it in that other form where they multiply that 2 in. But technically, guys, either one is right. And I kind of like this one because it's written in that form where all of our clues are super clear. So words, do we need to be scared of them?
No.
Not really. It kind of was a little bit clearer than the picture that we had to figure stuff out from ourselves. Okay, so maybe some of these ones that are having us dig a little deeper maybe aren't necessarily all that bad, as long as we just think of, what did I do in both of these problems? What did I start with? The general equation, and then picked out my clues. Okay, so we're not going to spend forever on this one. I just wanted to give you guys a peek at how sinusoidal curves could be applied. And this one is to the respiratory cycle. Why?
Okay, that's.
If you're not, you're breathing is a sinusoidal curve as well. But when you're talking about air going out, that's like the wave going up, and then air coming in, that's the wave going down. And then it does what?
Repeats.
Repeats. Hopefully. If it doesn't repeat, we're in trouble, right? So then coming back. They give us the following information. Oh, hey, look, it's a sinusoid. After exercising for a few minutes, a person has a respiratory cycle for which the velocity, how fast, the velocity of airflow is approximated by, equation. T is seconds, inhalation happens when V is positive. I did it backwards, sorry. Inhalation, you're breathing in air, that makes sense. Then exhalation, you're pushing it out. Velocity is positive, velocity is negative. What? I'm not going to go crazy in solving this, but I just want you guys to help me translate. When it says find the time for one full cycle, what are they actually having you find in terms of our special, the sinusoidal axis, the amplitude, the period, the initial point? The period is the one that tells us how long or how far for one cycle. So really all they're saying is, hey, plug into the period formula. Plug what in?
1.
Oh, who's B? Who's B, guys? Can you tell?
Pi over 2.
Right. What's being multiplied? Pi over 2. So we would plug into the formula, and we'd solve for, another way of saying that snazzy part is just find the period. Now, letter B is a little different. That's why I wanted to show you guys this page. There is one extra little clue we haven't really had to do because it doesn't really help with graphing. However, it is helpful in application problems. When it says find the number of cycles per minute, so each minute, how many cycles, like how many inhalations, exhalations you should have gone through. That is a snazzy way of saying find the frequency. And this is one I think you might have seen in Precalc. Just for a little bit. I said Precalc, not algebra 2, sorry. Frequency. It is a part that we didn't really need it for the graphing, but it does come in later. So if I were you, I'd probably write down just a quick little note to yourself. Frequency, who is that? Oh, that's how many cycles per unit of time. And what's the way that you find it? The formula, frequency just equals 1 over period. If we were to write it in a little equation. Frequency is just 1 over period. And then how would you sketch? Well, kiddos, isn't this a sinusoid? What's the one thing I didn't write that we might want for our little graph? Who's our D? Yeah. The one thing I didn't show the first time was 0. You guys can graph that. It's going to be a little funny because you're going to have like 1.7 up, 5 up, 1.75 down. But I think you could do it. We just sketch the graph. Okay, I'm not going to go in any more depth for this one. I just wanted you guys to see if you did have an application problem, the wording might point to one of the clues that we've been talking about. The one new one was frequency. I wanted you guys to get that formula down for how to find it. Okay, with that, section 4.5. What's the main point of 4.5? Can you graph a sinusoid? Wait, which trig functions have sinusoidal curves? Sine and cosine.
Oh no. What about tangent?
How many trig functions are there?
6. Or technically 9. Well,
Okay,
sine
Struggle.
minus 1.
we've done how many of them? 2. How many more do we have left? 4. Well, that's crazy. So we probably have like, what, 2 more sections for, oh my goodness, they put it all in one.
That's easy.
Now, we're not going to spend forever because they actually kind of work together. Did you guys notice how sine and cosine were kind of related? Right? Their graphs were super similar, just a few differences. And for sine and cosine, the only difference is where you start. Sine or top. It's the only difference. for sine and cosine. So what do you think about tangent and cotangent? They're going to be similar, but maybe have a couple differences. How about secant and cosecant?
Similar.
Similar with a couple differences. Similar but with a couple differences. Now, normally I start off with tangent and cotangent. Can't think this time.
Start this tomorrow.
Oh, no, we can't do that. We're supposed to actually have a full day on this, but we'll have a half day on it. Let me still go ahead and start with tangent and cotangent, but let me tell you the following. As you're striving, as you're working to finish 4-5 tonight, if you can get really good, or at least somewhat good, at graphing sine and cosine. Hold on, pencils down, I know you're all focused. Let's look back up. As you're working on homework tonight, if you can get really good at graphing sine and cosine, guess what's going to come easier? Not those ones, but cosecant and secant. They go hand in hand. If you're able to do the sine and cosine curves, secant and cosecant is not going to be hard at all. So we're going to go ahead and cover the harder ones, the newer ones, tangent and cotangent. We're going to try and cover those today. Then we're going to kind of recap on tangent, cotangent tomorrow after grading homework quickly, I should say. Then we're going to see how cosecant and secant just use sine and cosine and do a couple extra things. Okay? So, please, 4-5 is super important. He's the foundation kind of to all the rest, especially to the secant and cosecant ones. So let me save the secant and cosecant until tomorrow. You guys will work on your sines and cosines tonight. Good? Game plan? Set?
It's called audible.
Tangent. I don't want to go into tons and tons of depth, but I do want to at least go back to the unit circle for a couple seconds. So if I were you, I would pause on writing this stuff and I would just come right back up here to the review. I've drawn a little baby unit circle, and I want us to talk about tangent at a couple different places. First of all, tangent is technically in our unit circle, isn't he y over x, right? Opposite over adjacent, sine over cosine, however you want to think about it. So if I look at tangent of 0, I have the point 1, 0. Question, what is tangent of 0 again? When you think about it, you can be careful.
Oh, no.
Remember your table? Undefined's over here. Who's here?
1, 0.
0. Square root of 3 over 3, 1 square root of 3, undefined. Okay, so 0 is first. Why? We'll take the y over the x. What's 0 over 1? So tangent of 0 is 0 over 1 is 0. Oh. So when the angle is 0, the tangent is 0. Guess what that means down here from my graph? Tangent has a point at 0, 0, just like, who else has a point at 0, 0 when it's not transformed?
Sine.
Sine. Just like sine. Let's go to another special one. We can go to all the other ones. Maybe we'll go to pi over 4. Remember pi over 4? He has square root of 2 over 2. What's special about tangent at pi over 4?
It's 1.
It's 1, right? So I could come down here to the graph and I could put pi over 4. And I could put 1. So it looks like tangent's going up, right? What's tangent at 90 or at pi over 2 when my point is 0, 1? Oh. Now, up to this point, whenever we did undefined, I was like, oh yeah, it just doesn't exist. Error, just forget it, right? Ignore it. It's nothing. It's actually not nothing. It means something. What it means is a vertical asymptote. The slope is infinite. We kind of talked about that before. Remember the infinite slope, you're going to die if you try skiing that one? As opposed to flat slope, you'll be fine, just boring. Undefined. At pi over 2, tangent has what sine and cosine did not have. It has a vertical asymptote. Now, if we were to go on the other side, so it seems like tangent is increasing, and to be honest, it really is increasing. But if we were to go the other side, if we were to go negative, well, tangent was positive in the first quadrant, he's negative in the second quadrant, but otherwise things repeat, like negative pi over 4 is going to be at negative 1. And negative pi over 2, well, he's going to have a vertical asymptote also.
So these are gonna be really boring to grab.
There's not a lot going on.
Woohoo!
There's not a lot going on. Now, hold on, there is something important that I need you guys to see. Did I graph a straight line? I would have to do some more points, which none of us probably want to do. But I'd have to do some more points to show you it really does curve up like a cup, concave up here. And it curves down like a frown, concave down over here. So it does have a little curve. It has a point of inflection in the middle. But otherwise, well, tangent's not all that exciting. But he does have some parts we need to talk about, like vertical asymptotes. Tangent is going to have vertical asymptotes at pi over 2. I'm going to put the first vertical asymptote. It's just going to kind of help us with graphing. The first vertical asymptote is going to be at x equals pi over 2. And then normal tangent, well, let me get back to the others in just a second. But the first vertical asymptote is going to be at pi over 2. The others we'll get back to in just a second. Can you guys tell by looking at tangent, if that's one cycle right there, how long is he? How long is his period? His range is infinite, but his domain, half pi makes whole pi. How is that different from sine and cosine?
Could be anything.
Well, sine and cosine, what were their periods? 2 pi. So tangent's half that. Tangent repeats every half unit circle. So tangent's period is going to be pi. Now here's how that's helpful. If we can find our first vertical asymptote, we can add the period to find another one, or we can subtract the period to find another one. Meaning, if I wanted to graph another tangent, I'd have to go the period again. I'd have to add pi. And 1/2 pi plus pi would be 3/2 pi. And I could say, hey, you know what? There's another vertical asymptote over there. Or if I wanted to find another cycle, I could go backwards pi. And then I'd have to find, once again, the middle point, which this one's nice, he's just at pi. And I could graph another one. It's a little bit harder to graph another tangent than it was to graph more sine and more cosine. But there is a pattern. So how do we find the other vertical asymptotes? Here's a snazzy way of writing it. We start at the first one. Careful, don't add half a pi. Add the whole period, which is 1 pi. And we put a snazzy pi times n. Now that sounds kind of weird. We add pi n because we could add 1 pi or 2 pi or 3 pi's and we'll get vertical asymptotes every time. Or we could subtract 1 pi if n was negative 1. So n equals counting numbers, negative and positive, to show that technically they're integers, right? So that's a little baby formula because how many vertical asymptotes are there? Infinitely many. How come? Tangent just keeps cycling. Just like sine and cosine, but the graph is different. Domain and range, oh, they're way close together, I apologize. Domain, x cannot equal the vertical asymptotes, but everything else is fine. Range, you guys said this a second ago, actually. How high, how low does it go? Yeah, it goes infinitely low and infinitely high. And symmetry, if you look at it, it has origin symmetry, which means it's odd. Okay. That's tangent. Now, we're probably not going to get to cotangent today, but I want to show you what happens when we change tangent, when we transform him. But remember, if we can get tangent, he was probably a lot like him. Cotangent. So this is normal tangent. This is his normal information, his parent function. But then what happens when you transform? We're not going to go into as much detail about his transformations because, to be honest, he doesn't really have as much that'll change. He doesn't really have as much that'll change. He doesn't really have as much that can change. We're going to find vertical asymptotes first from the transform function. Then we're going to find what I'm going to call the point of inflection, which is actually that special point, which is halfway in between. And for the parent function, that's at 0, 0. We're going to find vertical asymptotes first, and then we're going to find the point of inflection, which is going to be that point halfway in between. And technically, as a part of finding our vertical asymptotes, we're also going to need to find our period. So that's going to be a little extra piece kind of off to the side. That's going to be important as well. Now, the nice thing about period, guys, is we get to use the exact same thing that we did with sine and cosine, except the only difference is when we do our 1 over b, it's not going to be times 2 pi anymore. So what's the period of tangent? Pi. So we have to go ahead and say 1 over b times pi instead of 2 pi. That's the one difference for our period. And how are we going to use him? Well, our first vertical asymptote is going to be at or when bx minus c equals pi over 2. Long story short, that bx minus c can change where our vertical asymptotes are. So if we just say, okay, whoever you are, whatever changes you're doing to tangent, whenever you're pi over 2, we got trouble. Whenever you're equal to pi over 2, we have a vertical asymptote. And then how do we find the others? We start from the first and we add the period. Oops, the period got away. So on the other page, we just had to add pi, but what if the period changes? We'll struggle. We'll have to add whatever the new period is. But we start from the first and then we add whatever the period is and we find another one. And we subtract whatever the period was. We find another one. We can find as many as we need. Now, points of inflection, they're the starting points. The nice thing is they're a little bit easier in that they always happen. Remember the original tangent was at 0, 0. We get to set bx minus c equal to 0. And say, hey, when you're 0, it's in the center. Bx minus c, we can set that equal to 0. Wait a minute, hold on. Can't we actually do that? That would be when x equals, right? Couldn't we add the c and divide by the b? Oh, yeah. C over b. For sinusoids, that was the initial. It's the initial for tangent, too. So we could just say c over b again. And technically, the y value would equal d, if there is a d. In tangent, there rarely is a d. But that would be the x and y. And then how do we find the others? We start from the first, and we add the period. We start from the first and add the period, just like we're going to do for vertical asymptotes. Okay, I think we're about done. Yeah. We got all the stuff for tangent. We're just going to play with a couple transform ones tomorrow. If you know tangent, you know cotangent, and if you work really hard on your sines and cosines tonight, you'll do fine on tangents and cosines. Okay? Yeah, you're going to work on that 4, 5 tonight. I did get new correction papers, so if you guys do need one, you can grab one on your way out. I'm writing practice yesterday. Bye, kids. Happy Wednesday.